Okay, for this second part of the video about load duration curve for the Cannon River, I want to illustrate or show you how we generated the sediment samples, because I'm doing this in a little bit different way in which than actually having real sediment samples, and the purpose is to show the effect of not having a perfect not a perfect relationship between discharge and TSS. Before I get started on that, I just want to make a correction to what I said in the last video, and that is that in calculating your percent exceedances, I made a slight change to that. There are 2,887 values that are good in the discharge data. There's more than that. There's about almost 3,000 values total, but there, like I said before, there's some missing data. There's some ice days where the flow measurement is not very good. So it turned out to be 2,887 values. And to calculate the percent exceedance, you should always leave a little bit of room for the largest value in the ranked numbers, so that there's always some probability that the largest value that you have measured does not have 0% of being exceeded. So you'll see here that what I've done here is divided by the rank by 2,888 instead of 2,887. And if you go down to the bottom of the data file, here's the largest value, 20,100 cubic feet per second. That's ranked 2,887. If I had divided the rank by taken 1 and subtracted the ratio of the rank divided by 2,887, this number would turn out to be 0. And that would mean that there would be 0% chance of exceeding 20,100. So if we divide it by 2,888, it gives me a slight probability that there would be a larger value than the 20,100. This is a normal analysis procedure that's used in ranking maximum flows and so on for flood probability analysis. Okay, so anyway, that's a simple explanation for that. So I've got all those rank values, and I already showed you in the last video the plot of the values. Now to come to the load duration curve. So there is a standard or a target value here. The target is given here as 25 milligram per liter. That's a good value for the southern part of Minnesota, but if you're up in the northern, let's say the Arrowhead region or something, Boundary Waters, then you probably use 10 milligram per liter, just a higher standard. And so what we do would be for every one of the discharge values that we've got in our flow duration curve, we would multiply those values, those discharge values by this mass, which is this concentration, milligram per liter, and with correction factor and so on to change the units, I would end up with a discharge of, or I'd end up with a load of kilogram per day. I could use a different unit than that, but the water quality standard then is given in this column. So for that discharge of, in this case, 139 cubic feet per second, the smallest value, I multiply it by 25 milligram per liter, do all of the unit changes and so on. This unit for the water quality standard is going to be kilograms per day, and so the value is 8,508. And of course, from this value on upward, as the discharge increases, the water quality standard value of the load associated with that flow also increases, as you might expect. So the shape of the plot of flow or I should say of percent exceedance versus water quality standard, will have the same shape as the flow duration curve. As I indicated in class, that graph will just be a scaled graph, or the line will be scaled based on the change in units. All right, so that will give us the water quality standard. I can go down here and show you that plot, which also has the sample data on it. We'll talk about the sample data in a moment. But this blue line is the plot of the line for the water quality standard. And you can see that that graph has the same shape as it has the shape of the curve for the flow duration curve. It's just a scaled, if you look at the vertical axis, there's a big difference in the magnitude of the numbers. Here we've got something on the order of 1 million. There we've got something on the order of about 20,000. So that's all because of the change in units from cubic feet per second, and then we multiply it by milligrams per liter and do the conversion of units to give us kilograms per day. Okay, so that gives us the graph for the water quality standard. And then normally what we would be working with, we'd have grab samples of sediment load, or sediment concentration in milligram per liter on particular days. Those might be randomly selected days or whatever. And I've generated here some sample values, as you can see. For instance, for this date here, we have a discharge, the sample flow, or the flow rate on the day of sampling is 155 cubic feet per second. There's that value. The concentration is 3.42. If I multiply 155 by 3.42, do the units conversion, I get 1299 for the kilogram per day on that day. The next sample, which was 10 days later, was 158 cubic feet per second. Do the multiplication times 2.81, and I get 1085. All right, all these other numbers in here, the 0.01s and so on, are all artificial. They're values that don't really mean anything. They're only in there because, for some reason in Excel, I don't know how to make the plot unless I have all the rows filled in. So I put a 0.01 in there for dates when I don't want to have a plot made. It's only going to plot the values that are greater than this 0.01. All right, so these are treated as being sample dates, and I just arbitrarily chose it so that we would choose a increment of 10 days between samples, and that can be modified right here in the spreadsheet. If I change this to 5, I get a value every 5 days. If I change it to 20, I get a value every 20 days. Right. So we'll go back and leave it with 10. All right, so these sample values that you see here are randomly generated. You see the 4.013 here. The actual generated value of the sediment is given here. And I'll explain now how that is calculated. So what I assumed here was a slope for the relationship between TSS and discharge. It has units of milligrams per liter per cubic foot per second. So I assumed a linear relationship between TSS and Q. That linear relationship would just have the form of a straight line. Y is equal to mx plus b, where m, the slope, is equal to 0.02. X would be the discharge rate, and b would be some intercept. Here I assume the intercept is equal to 0, so the graph should go through the origin of the plot. All right, so maybe it's easiest if I just change this. I'll explain what this 10 is here in a minute. I'm just going to put a 0 in there for right now. And basically, this plot of this graph shows here the relationship between discharge on the horizontal axis and TSS. So the slope of that line is 0.02. And you can see it's a perfect straight line for the relationship between sediment concentration milligram per liter versus discharge. Okay, so I hope that's clear. I'm going to go back in here and put a 10. All right, so because of the fact that there is no perfect relationship between TSS and Q, generally there's some randomness that it's not a perfect straight line, it's not a perfect nonlinear line or anything like that. There's some randomness around a best fit line. I've got here, I'm basically generating the sediment data for any particular date using a random number generator. The random number generator is based on using a uniformly distributed random number between 0 and 1. The random numbers are given in this column right here, and all these numbers that you see in this column I range between 0 and 1. The argument for a random number generator is equals rand of, and there's the argument inside. You don't actually have to put a number in there. This will generate a random number between 0 and 1. That random number is then multiplied by standard deviation, which is the number that I've got here in this row. And that standard deviation is 10 milligram per liter. This is going to give us an idea how much magnitude variation there is between the straight line relationship between TSS and Q and some deviation off of that straight line. Basically, you multiply the standard deviation times a random number, add it to the value of TSS that you would get based on the Q value. So, for instance, here the discharge is 155 cubic feet per second. I can multiply that by 0.02, and that would give me a value of TSS. What would be about 3, something like that. Yeah, 3. If I multiply that out, it'd be exactly 3.3. And then if I take the random number of 0.6 and I multiply it by 10 and then add it to this, I get 3.44. Okay, so that's the randomly generated value of sediment concentration. And then I have some algorithm in here that just basically generates them for every day. And then I have this algorithm that only chooses the ones every 10th day. And that's why you can see here, there's one that's chosen right here, and then there's one 10 days later that's chosen. And this is all artificial, but it's just a way to illustrate the effect of this uncertainty in the relationship between TSS and discharge. So with the standard deviation of 10 milligram per liter, you can see instead of a perfect straight line, which would go from the origin on up at a slope of 0.02, we have a variation, and the variation is a function of the magnitude of the flow. So you can see that there's quite a big spread of the data around the best fit line. So I could put a trend line through here, and I'll do that here. I think I'll do it anyway. Yeah, here we go. Trend line. And you can see what that trend line is. It has a slope of 0.02 or approximately equal to 0.02. And if I were to go back here and change this standard deviation to 0, you'd see all the points would fall right on that trend line. Okay. And I can make this standard deviation as large as I want. Obviously, at some point, it gets worse and worse. But in the assignments that you'll do, you'll find that you will not have a perfect relationship between TSS and Q. And I'm trying to illustrate the effect of this on your load duration curve and your estimate of the loads. One other thing that's given here are some statistics on the flows. So the maximum flow is 20,100 cubic feet per second. and the mean flow is 936. That's using all the flow data in the data set. A plot of discharge versus time, and also sediment concentration versus time is shown here. The blue dots are the discharges, and the red dots are the sediment concentrations that are generated from the random number generator on dates. Every 10 days, one sample is taken. Okay. All right. So now the sediment load is calculated by taking the sediment concentration, in this case 3.97 for this one, multiply 3.97 times 155, and then we do the units conversion to give us kilograms per day, and that value is 1505. Take 158, multiply by 2.52, the units are kilograms per day at 975. Okay, so I can then plot the sample values, I should say the discharges versus the sediment load, or here we would plot percent exceedance corresponding to the sediment load. So for instance, for this one here, it would have a fraction of exceedance of 0.9965. And the plot would be 1505 on the vertical axis. So here I've got plotted on here the load duration curve for the target. And then you can see that all these points are scattered a bit. Still looks pretty good, but I could fit a line through those. Also shown on here are the mean values at any given exceedance value, the maximum value, the minimum value, 25% quartile, 75% quartile. 75% just basically mean 75% of the values are at any given level here or less than that value. 25% means 25% of below. The median value is also plotted. Median just means 50% of the values at any given level are below that value. Okay. So what we can do is we can play around with that standard deviation. If I make the standard deviation 0, you can see that basically the points all fall on a line. The maximum minimums and so on that are shown here are a bit deceiving because these are calculated over a range of values. So actually there should not be any variation in, all these points should fall on the same location on the graph at any given exceedance level. And I haven't figured out how to fix that. But in the assignment, you're going to be asked to calculate the load, the median load, and the 25% and the 75% load estimates to come up with a range of estimates of the load. So the point here is that the larger the standard deviation, let's say if I make this 20, we get quite a large spread in the upper and lower limits. You can see the amount of spread here, and the larger the spread between the maximum and minimum, or between 75% and the 25%, the larger will be your error of estimate of the mean loading rate. And if there is no standard deviation, or I should say, if the fit between TSS and Q is perfect, then your estimate will be perfect. There would be no uncertainty in your estimate. Of course, that never really happens in real life. One other thing in this spreadsheet, this table down here is used to calculate these different parameters. The median, first quartile, third quartile. The first quartile would be 25 percentile. Third quartile would be 75%, maximum, minimum, and mean values. And so that's just set up to do that kind of a calculation, so that those can then be pretty readily plotted. Now, this spread of these lines, or these different values here at different percent levels, that's usually referred to as being a box whisker plot, although I don't have the box on there. But basically, a box whisker plot would show a range of values, the median, the 75% quartile, and 25% quartile. And also it would show usually the 10% and 90% quartiles. Okay, so with that, I think I've completed what I wanted to show here, illustrating the effect of the imperfection in the relationship between the concentration of a constituent and the load.